If we run an experiment where we look at the initial concentrations and the equilibrium concentrations of a chemical reaction, we'll notice that the equilibrium constant, comparing those equilibrium concentrations, is the same no matter what concentrations we start with. We'll also notice that the reason that this is because there is a stoichiometric relationship between how those concentrations change. So if we look at H2 and we add 0.5 molar of H2 and 0.5 molar of I2 in our reaction vessel, it will change those concentrations equally to form a concentration that is twice the amount of change. So if we look at 0.11 or 0.50, sorry, minus 0.11, our change between the two is 0.39 molar for both of the H2 and the I2. The HI that is formed is 0.39 times 2. And this is because we have 2 HI that is formed for every hydrogen and iodine molecule that is used. If we compare all of the reactions that are shown in these different experiments, we'll see this similar trend as well. And again, our equilibrium constant remains the same no matter what our initial concentrations are. Let's look at a theoretical equation to try and figure out how the stoichiometry helps us determine our concentrations. So we're going to look at a reaction that we have 2A plus B giving us 4C. So frequently it's helpful to lay out a table with the information that you're given. So our initial molarities before the reaction starts are 1 molar for A, 1 molar for B, and because the reaction hasn't progressed at all, there is no C produced yet. If we measure the equilibrium concentration of C, we're told that it is 0.5 molar. We're going to set up a table, and we call this an ICE table. So ICE stands for initial, change, and equilibrium. So our initial was 1 molar A and B. Our equilibrium is 0.5 molar C. So let's look at our change in concentration. So for C, our change in concentration, we gained 0.5 molar over the course of the reaction. Because we have 0.5 molar C, we can calculate what the concentrations of B and A changed by. So 0.5 molar C, it took 4 moles of C, or we produced 4 moles of C when we used 2 moles of A. And so our ratio, we're decreasing A because we're using up the reactants by 2 over 4, which is 1/2. So we're decreasing by minus 1/2 times the change of C. For B, because it was only 1 mole of B to produce 4 moles of C, we're decreasing, which is why it's negative, 1/4 of the change of C. And we can calculate our equilibrium molarities for A and B. So 1 minus 1/2 of 0.5, which would be 0.25, is 0.75 molar left of A. 1/4 of 0.5, if we subtract that from our initial concentration, we end up with 0.88 molar B. in order to have our equilibrium concentration of C of 0.5. Let's look at an example where we're taking methane and producing ethine and hydrogen. We're given the initial and equilibrium concentration. Let's construct an ice table for the reaction. We're going to input our initial concentration of methane and the equilibrium concentration of the ethine. We can determine the change in equilibrium concentration for the ethine. Because it's a product, it's going to be positive. We started at 0, and so it changed in concentration by 0.035 molar. We can use that known change to help us calculate the other concentrations using our stoichiometry. So our H2, we know that the change was 0.35 molar. We can use the stoichiometry from our balanced chemical reaction to find the H2 and also our methane. So for H2, our change is going to be 0.105 molar of H2. For our methane, starting with the concentration or the change of our ethine, 1 mole of ethine requires 2 moles of our methane. So its change is going to be a negative 0.07 molar. So to find our equilibrium concentration, we're now going to add the initial plus the change. So 0.115, and because we're adding a negative, our concentration is going to decrease for the methane. For the H2, we're going to add the initial plus our change. Because it's a product, it's going to increase. And we now know each of those equilibrium concentrations for all of our products and reactants. This allows us to calculate our Kc. It's going to be equal to the concentration of the products raised to the coefficient divided by the reactants raised to the coefficient. We can plug in the values that we found at equilibrium. To find our equilibrium concentration. Or equilibrium constant, I mean. Oops, sorry. Let's try that again. 0.02 would be our equilibrium constant. This value is less than 1, which means that our reactants are favored in this chemical reaction. Here's a practice problem for you to try. See if you can complete the table and determine the values of Kp and Kc. Pause the video while you determine your answer. Let's start with our equilibrium concentration that were provided. We want to find the change, and so we can subtract the initial concentration and the equilibrium concentration and find that it is a value of 0.0028. Our concentration has decreased, and so our change is negative. To find the change of N2O4, we can use stoichiometry. So we start with the change of our NO2. We know it takes 2 moles of NO2 to make 1 mole of N2O4. So our change for N2O4 is 0.0014, half of the change of NO2. Because it's a product, it's forming, and our concentration is increasing. Because we started with 0 moles of our N2O4, our equilibrium concentration is 0.0014 molar. To find our Kc, we need to write our equilibrium constant expression. Products divided by reactants, remembering to raise it to the power of the coefficient in the chemical reaction. Now we can plug in our concentrations that we found in the table to find our Kc. Oops, sorry about that. This isn't the change, this is the equilibrium concentration squared. We end up with a value of 4.7. To find the Kp, it is the equilibrium constant for concentration times R times the temperature raised to our change in the number of moles. So if we plug our values in, 4.7 times 0.08206, 100 degrees Celsius, so 100 plus 273 is 373. Our change in moles, so products is 1 mole minus our reactants, which is 2 moles, for a change of -1 moles. And so our Kp is 0.15.